Okay, so this lecture is going to build on the flipped class video of the same name. So let's recall from that video, we saw that the derivative of a function, say y is equal to f of x, at say x equals a, is given by, well, remember this was the limit of the secant line, so we wrote this as f prime of x. Is one version of this was the limit as h goes to 0, or f prime of a, excuse me. So the limit as h goes to 0 of f of a minus f of a plus h minus f of a over h. So this is the limit definition. There's one way to say this, or we can also refer to this as the difference quotients. So if you're asked to find the derivative based upon the limit definition of the derivative or based on difference quotients, you're taking this limit here. Okay, so we say f is differentiable at x equals a if this limit exists. So remember, for that we have to check the limit coming from h coming to 0 from the right and the left. And finally, we know that this is giving the slope of the tangent line. So we have the tangent line, has the point a f of a and slope f prime of a. So it's given by, we can put it in point slope form, so y minus f of a is equal to f prime of a x minus a. And so that's our tangent line. So let's go ahead and work some examples. So let's find the tangent line for, let's take our function f of x to be, say, 2x plus 1 over x plus 3 and find the tangent line at a equals 2. So we saw some simpler examples than this in the flipped class video, but for us, let's go ahead and start off with something that's a little bit more complicated. So the first thing we can find is, since we're trying to find a tangent line, we need a point on the line. So note that I want the value f of 2 for that point on the line. So this is 2 times 2 plus 1 over 2 plus 3. And if we simplify that, we just get 1. So our point on the tangent line is 2, 1. So that'll be important when we go to actually give the line itself. So now what we need to do is we need to find the slope. So we need to find f prime of 2. If we have a point and we have a slope, then we have the line. So let's do that calculation. So if we use the limit definition of the derivative or the difference quotients definition, I'm looking at this limit right here. So let's go ahead and plug in for what our function f is. So if I recall that my function is 2x plus 1 over x plus 3, so this will be 2 times 2 plus h plus 1 over 2 plus h plus 3. And we just calculated f of 2 is equal to 1, so this is just minus 1 all over h. So now we need to simplify this. So this is going to require a bit of algebra here. So let's take this 1 over h and just write this like this while we do our simplification. Now let's go ahead and FOIL that 2 through. And let's simplify the bottom here as well. So this is just h plus 5 and then minus 1. And now to simplify this, we want to get, well, we can do one more simplification in the numerator there. So that's a 5, or let's write it as 2h plus 5 over h plus 5 minus 1. And now to simplify this further, we want to go ahead and get a common denominator. So let's leave this 1 over h alone for now. So I'm going to have 2h plus 5 over h plus 5. And then to get a common denominator, we multiply the top and bottom by h plus 5. And now it's just a matter, at this point, of just simplifying with algebra. So I'll bring these together, and I'm going to have a 2h plus 5 minus h minus 5 over h plus 5. And if I simplify that, I have this 1 over h. Now notice I have 2h minus h, so that'll give me h in the top. Those 5's cancel, and I get h plus 5 in the bottom. So now I can cancel the h in the top and the bottom, and this just becomes the limit as h goes to 0 of 1 over h plus 5. And we can evaluate this limit by just plugging in 0, so I get 1/5. So recalling that our point was 2, 1, our tangent line, we write this in point slope formula, so this is y minus 1 is equal to 1/5 x minus 2. So that's how we go ahead and do that calculation for our tangent line. So you can see, once we get this definition down, it's really just a matter of doing a bunch of algebra to simplify everything so that we can cancel those h's out. Once we cancel those h's out, the limit's very easy. So let's try another example. This time we'll do a word problem. Okay, so we'll say the cost given in dollars of producing X units of some product, doesn't matter what the product is for this problem, just some product, is given by this function. Okay, we want to ask some questions about this. So for the first one, let's find the average rate of change. So this is slope of a secant line because it's average change. So we'll do this with respect to X when the production levels are changed So for the first one, let's go from x equals 100 to x equals 105. And for the second one, let's go from x equals 100 to x equals 101. So these difference quotients here, it's the average rate of change here should be c of 105 for part 1 here, minus c of 100 over 105 minus 100. And so we fill these values in, and so I'm going to have 5,000 plus 10 times 105 plus 0.05 times 105 squared minus 5,000 plus 10 times 100 plus 0.05 times 100 squared all over 5. So I'm just evaluating it at 105 and 1, just plugging those into the function. And if you plug those in, you get 20.25. And now in terms of our units, we know that C is measured in terms of dollars. This will be dollars for the top, and then the X is measured in number of units. So dollars per unit is our measurement, or our units here. For the second one, we just do the exact same thing. We just use 101 and 100. So this is a better approximation for our instantaneous rate of change at x equals 100. So we do the same thing, 5,000 plus 10 times 101 plus 0.05 times 101 squared minus 5,000 plus 10 times 100 plus 0.05 100 squared. And now this whole thing is over 1. And if we simplify that, this is 20.05. And again, the units are dollars per unit. Okay, so that gives us our average rate of change. And now we can also ask for the instantaneous rate of change. So WRT is with respect to. At x equals 100. So for this, we want to calculate the instantaneous rate of change. So we want C prime of 100. So let's go ahead and use our definition to calculate this. This is the limit as h goes to 0 of C of 100 plus h minus C of 100 over h. Now this becomes a little bit messy, but not necessarily difficult. So I have 5,000 plus 10 times 100 plus h plus 0.05 times 100 plus h squared minus 5,000 plus 10 times 100 plus 0.05 times 100 squared all over h. And now if you FOIL things out and do all the cancellation, which we're not going to do here, it's just tedious, but if you do all that, you get 0.05 h squared plus 20h over h. So maybe pause the video at this point and do that calculation to make sure you agree with what I got and you see where it comes from. Now if I cancel an h from the top and the bottom, I get limit as h goes to 0 of 0.05h plus 20. As h goes to 0, that first term goes to 0, so this is just 20, and the units are again dollars per unit. Okay, so what we could say here if we wanted to interpret this, we're going to spend a little bit of time interpreting derivatives later in this unit, but what this would say is if I've produced 100 units, it would cost approximately, because this C prime is telling us how does the function change, it would cost approximately $20 to produce one more unit. Now in this case, if we believe that C of x is giving us the exact amount, we could actually calculate exactly how much it costs to produce one more unit by just taking C of 21 minus C of 20. But often you won't have an exact function like this, and so this derivative kind of tells you how things change. So how the cost changes as you change the number of units produced. So let's look at another example. So eucalyptus trees, these grow better with more water. So scientists found that the volume of wood that grows on a square kilometer of land, so measured in meters cubed, so the wood is measured in meters cubed, is approximated by this function. So V of r is equal to 0.2 r squared minus 20r plus 600. in R here, so volume this is measured in meters cubed, and R is the rainfall. So this is the annual rainfall in centimeters, where we're going to restrict ourselves to at least 60 centimeters and no more than 120 centimeters. Okay, so they modeled the growth, came up with this equation that gives us a good approximation for it. So let's do the same kind of things with this. Let's find the average rate of change. For V with respect to R over the interval 100 less than or equal to R less than or equal to 110. Okay, so same type of thing we've been doing. So the average rate of change, well, this is going to be V of 110 minus V of 100 over 110 minus 100. So if we plug those in, this is 0.2 times 110 squared minus 20 times 110 plus 600 minus 0.2 times 100 squared minus 20 times 100 plus 600. And 110 minus 100 is just 10, so I have a 10 in the denominator. And if you calculate that out, this gives 820 minus 600 over 10. So this is 22. And now remember, we want to figure out what the units are. So the volume, the top part here, this is measured in meters cubed, and the rainfall is measured in centimeters. So this is meters cubed per centimeter. So now let's go ahead and calculate the instantaneous rate of change. So let's calculate this of V at R equals 100. So again, we use the definition of the derivative here. So this is going to be the limit as h goes to 0 of V of 100 plus h minus V of 100 over h. One thing to be careful of when you're doing these calculations is it's important to be precise with our equalities. So you notice sometimes I write approximately equal to, sometimes I write equal to. The other thing that we want to be careful of here is you can't just arbitrarily include and then not include the limit. So if we're using equalities, we have to keep this limit in here while we're doing the calculation. Once we've evaluated the limit, it goes away. But you can't just arbitrarily put it in and take it out. You have to always keep it in for this part. If you want to do the algebra over to the side so you're not saying things are equal, that's fine. And now, remember we calculated above here that V of 100 is 600. So we get this. And so if we go ahead and simplify this, what we're going to get is the limit as h goes to 0. So do all the simplifications here. I get 0.2h squared minus 20h over h. I can simplify that 40h minus 20h to get 20h plus 0.2h squared over h. I can now cancel one of those h's out, so I get the limit as h goes to 0 of 20 plus 0.2h, which is just 20. And remember, this is measured in meters cubed per centimeter. Now we also saw in the flipped class video that it's useful to, instead of just calculating the derivative at various points, we can actually define the derivative as a function. So recall that definition basically it's the exact same definition, only instead of getting a number out of it, we're getting a function. So we're basically just replacing that a with an x so that we get a function here. Right, so this is a function. So you can plug different values of x into this. So let's see an example. There are some examples in the flipped class video, but let's see some more examples here. So again, we'll start with one that's not the simplest example because we've already seen some simple examples. So let's take f of x to be square root of x plus 2 and calculate the derivative as a function. So calculate f prime of x. So to do this, we just use our definition again. And again, you can, when you're asked to do this, if you're asked to use the definition, I'll often say use the limit definition of the derivative to calculate this, or we'll say calculate it via the difference quotients. So this is our definition, so let's go ahead and plug what our function is. So that means wherever there's an x, I'm going to replace it with x plus h. So that's f of x plus h. And sometimes this can look a little bit more intimidating because we don't have as many numbers in there. We've got x as a variable and h is varying as well, so it looks intimidating, but the more of these you do, the more used to them you'll get. So this is one of those cases where we can use this trick again. So I can write this as x plus h plus 2 minus square root of x plus 2 over h. And now we use this trick by multiplying the top and bottom by what we call the conjugate. So take that negative sign and make it positive. And again, we see things work out nicely because when I FOIL this thing out, when I multiply the first term of each on the top, I'll get x plus h plus square root of x plus h plus 2, and that'll square, so that'll get rid of the square root, and then I'm going to get plus square root of x plus 2 square root of x plus h plus 2, and I'm going to get minus square root of x plus 2 square root of x plus h plus 2, and then the last term I'm going to get minus x plus 2 because those square roots will cancel out again, and then on the bottom I have this in the denominator. Now notice in the top those middle terms cancel, which is precisely the reason we multiply by the conjugate to get that cancellation. So I have x plus h plus 2, middle terms are gone, and now I have minus x minus 2 all over x times, or h times square root of x plus h plus 2 minus square root of, or sorry, this should be a plus square root of x plus 2. So we multiply by the conjugate, so the bottom becomes positive. Now notice the x and the 2 in the numerator cancel. So I'm just left with an h in the top, and then I have the h in the bottom as well. And then I still have this square root of x plus h plus 2 plus square root of x plus 2. Those h's will cancel out. So now I just have the limit as h goes to 0. On the top I have 1, and on the bottom I have x plus h plus 2 plus square root of x plus 2. Now when I evaluate this with h equals 0, I get square root of x plus square root of x plus 0 plus 2 square root of x plus 2. And now there's 2 copies of this, so I get 1 over 2 square root of x plus 2. And that's my final answer. Okay, so we can also graph the derivative to see what it looks like since we're considering it as a function. So let's see how that works. So let's consider a function Okay, so let's suppose my graph looks something like this. Comes down, comes back up, and comes, I want it to come down again. I want it to come down somewhat nicely though. Like this. So let's say this is y equals f of x. And let's say this value here is 1, this value is 2, minus 1, minus 2. And now let's graph f prime of x. And now I didn't give any values on the y-axis, which is not going to be important. We just want to get the shape of what f of x, or f prime of x looks like. So notice that, as we saw in the flipped class video, what we're asking for is the slopes at these various points. So we see x equals minus 1 and 1, f prime of x is equal to 0. And because remember, the derivative is the slope of the tangent line. So if I draw the tangent lines here, they're just horizontal lines. So those have slope 0. And between minus 1 and 1, my function is increasing. So no matter where you draw your tangent line here, the slope is always positive. So we get f prime of x is bigger than 0 for x, for minus 1 less than x less than 1. And similarly, if we're less than minus 1, it's decreasing, so the slopes of those tangent lines are going to be negative, and similarly when we're bigger than 1. So if we plug all that information together, so let's get these things on here. So the first thing I'm going to want to do is I'm going to want to use and fill in where is my graph equal to 0 at. So I know that it's equal to 0 at 1, at negative 1 and 1. And I also know, if I look at the graph, it's positive everywhere between minus 1 and 1, but it looks like it's the most steep here at 0, because then it starts flattening out again. So I'm going to figure the biggest value is going to be here somewhere. So it's going to go up to get to here, and then it's going to turn around and come back. And we also know on the other side of this, it's always negative, so it's going to look something like this. So that's how my derivative looks for this. Okay, so what we want to think of as we're doing this is we're just going through and looking at what is the slope of the tangent line at each point, and that slope is telling me what the value of the derivative is. Okay. So let's try some more examples of various ways the derivative was going to show up. So let's try another word problem. So we're going to look at the concentration of a drug in the bloodstream, and this is going to be in micrograms per centimeter cubed at time t, and t is going to be measured in minutes, is given by the following table. Okay, so let's get our table down here. So this is t, measuring this in minutes, and here's c of t, and this is going to be in micrograms per centimeters cubed. So this is my concentration. And let's put some values in here. So let's say this is 0.84, 0.89, 0.94, 0.98, 1, 0.97, and 0.90. So let's use this table to estimate values for C prime of t. So for the derivative, so how is the concentration changing as the time changes? So we'll use our difference quotients to estimate this. So C prime of t is approximately C of t plus h minus C of t over h. And now we can come at this and we can look at these various difference quotients. So if I look at C prime of 0, this is approximately, well, let's go one up. So let's go C of 0.1 minus C of 0 over, let's do 0.89 minus 0.84. And this is about 0.5. And the units here are going to be micrograms per centimeter cubed. That's our units of C. And then the units of T are in minutes. And we can continue to do this for each one. So C prime of 0.1 is approximately C of 0.2 minus C of 0.1 over, oh, I wrote this wrong. So this should be, let me rewrite this, messed that up there. So this should be C of 0.1 minus C of 0 over 0.1 minus 0. And this should be 0.2 minus 0.1. And so notice this is, let's go ahead and fill those values in just so we see them. I should have wrote these in for the first one as well. And this is again 0.5 micrograms per centimeters cubed per minute. And we could calculate this from the other side and average it. Sometimes we do that, sometimes we don't. Doesn't really matter when we're just estimating. So if we continue like this, for this case, we're just trying to get an idea of what's going on here. Let's fill these in. So I just calculated this is about 0.5. Also 0.5. So those are our approximate values of the function. And we could also graph our different values if we wanted to graph the table of values from above. And we want to compress our line here a little bit. So this is, say this is 0.8, 0.9, 1.0. So these are our values for C of t here. And then we can go 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. That's as far as we went up, was to 0.7. So these are t. And then we can graph these different values. So here we were about 0.84. And here we were about 0.89. And then we went to about 0.94. And about 0.98. And then I missed one here. 0.84, 0.89, 0.94, oh, this was supposed to be a 0. Oops. That's where I messed that up. Okay, let's redo this. And let's use a different color while we're at it. Okay, so we were at 0.84 at 0. And then at 1, we were at 0.89. At 0.2, we were about 0.94. And then we were about 0.98. And then at 4, we were at 1. 5, we were at 1. And then we were down at 0.97. And then about 0.90. So those were our measured values of C of t. So we can connect those to kind of interpolate what the graph should look like. So it should look something like this. It's going up, and then it's turning around and coming back down. Something like this. And this is about what our graph, and you can see the values of c of t or c prime of t there. They're not exact, they're approximate. So unless the graph happened to be completely flat between 0.4 and 0.5, no, sorry, 0.4 and 0.5 were the same values, most likely the graph went up a little bit and came back down. So somewhere in here is probably actually where our c prime of t is equal to 0. Not necessarily, we wouldn't expect it to be flat going from 0.4 to 0.5. Especially because at 0.5, the derivative is negative, so it should be decreasing at that point, not flat. Okay, so let's try another example now. This is going to be matching some scenarios with some graphs. So let's start with our example here. So let's say we have a vehicle moving along a straight line, or a straight road. And let's say this has distance d of t from its starting point at time t. So let's match the graphs of d prime of t with the correct scenario. Okay, so let's write our scenarios down first. So let's say a bus along a popular route with no traffic. That's our first scenario. Our second scenario is a car with no traffic and all green lights. And finally, our last one is a car in heavy traffic. Okay, and now let's graph our possible graphs. And these, remember, these are of the velocity. Okay, so our first graph is going to look something like this. Second graph maybe looks like this. And our third graph looks something like this. So let's think about what each of these is telling us. Remember, these are the graphs of the derivatives. So remember, as we're going along here, what is this telling us about our velocity? This first one is saying we start with a 0 velocity and then it continually increases, but it looks like it kind of levels off. So maybe we're getting some asymptote here, up here at some value. So I can think of this as a vehicle that's speeding up until it gets to kind of a set speed, and then it's going to stay around that speed. So I'm going to think of this as a car with no traffic and no green lights. It's just going to accelerate and keep speeding up until it gets to the speed limit, and then it's going to stay around that speed limit. For the second one, it looks like we're speeding up, hitting kind of a maximum velocity, and then slowing down, stopping for a bit, speeding up, hitting a maximum velocity, slowing down, stopping for a bit, and so on. So that seems like a bus on a popular route with no traffic. And then the last one, the velocity is kind of all over the place. It's speed up, slow down, speed up, slow down. So I'm going to view that one as a car in heavy traffic. So we can kind of read off what we're getting here by these different graphs. Okay, so let's try another example here. Okay, so the water temperature affects the growth rate of brook trout. So let's say the following table shows the amount of weight gained by a brook trout so brook trout is a fish after 24 days at various temperatures. Okay, so here's our table. So these are temperatures in degrees Celsius, and where weight is going to be gained in grams. So if we have 15.5, 17.7, 20, 22.4, and 24.4, and this is 37.2, 31, 19.8, 9.7, and minus 9.8. Okay. So let's let Wx be the weight gained at temperature X. So we can use the table to estimate values for W prime of X. And so let's see a few ways to do this. So for the first value, so W prime of 15.5, well, I don't have any values lower than that value. So for this, I'm just going to have to use the value from above it. So notice this is approximately equal to this average change here. So then I'm going to have the 17.7 minus the 15.5. And so if we calculate this out, well, this is the 31 minus 37.2 over 17.5 minus 15.5. And this comes out to be approximately negative 2.82. And what are our units here? Well, the weight, the W is measured in grams. And remember, the X is the temperature, so this is measured in degrees Celsius. So this is negative 2.82 grams per degree Celsius. Now for the other values, we could continue to just use the ones next to it. We could also do difference quotients on each side. So I could say W of 17.7 minus W of 15.5 over 17.7 minus 15.5. Well, that's what we just calculated. So we already saw this is negative 2.82 grams per degree Celsius. And in terms of our table, I can say if I'm estimating the W prime of 17.7, I can use this value and this value, or this value and this value together. So different sides we could use the secant lines of. And so I could do the same calculation on the other side. And if I do this, I get approximately negative 4.87 grams per degree Celsius. And so I could estimate that W prime of 17.7 is about the average of these two. So this is about negative 3.85 grams per degree Celsius. And so if we continue in this pattern, again, when we get to the last one, we'll only have one to check because we don't have both sides. So maybe at this point it'd be a good idea to pause the video and try to do these calculations on your own and make sure you get the same values that we get that I'm going to give you here for the table. And so W prime of X, this is measured in grams per degree Celsius, and this is approximately the values given here. So I have the same values of temperature as my table above. So these are the two we calculated, and if you continue to do the same process, we would get these values. So we can see from this, as we could see from the table above, the most it gained was when the temperature was 15.5, and then it started going down from there. But we actually noticed not only did it start going down from there, we didn't even gain, not only did we not gain anything at 24.4, we actually lost weight gain. And we see that here where no matter what we do, as we're going up, the derivative is always negative because our weight gain is going down as we increase the temperature, and it goes down by the most at the highest temperature. So now that we have some experience with calculating derivatives and doing some word problems and estimating the derivatives, one more thing that's very important to be able to do is we need to be able to interpret what we're actually learning from our derivatives. So we're going to do this with a couple examples here to help us on interpretation. So let's suppose we have an economist, and this person's interested in how price of a certain commodity impacts its sales. Okay, so if I change the price, how does that change how many items I will sell? Let's suppose our price is given in P. Let's suppose the price is P, and this is measured in dollars. And it's related to the quantity sold by some quantity sold. We'll say that quantity sold is given by Q. Q is equal to f of P for some function f. We're not going to say what the function is, just there is some function there. So let's interpret the following pieces of information. So the first one, what does it mean for f of 10 to be equal to 240,000? And secondly, let's interpret what it means for f prime of 10 to be equal to minus 29,000. So the first one is just directly the price impacting the quantity. So for the first one, f of 10 equals 240,000. Well, the 10 is the price, and the 240,000 is the quantity sold. So what does this say? So one might interpret this and say, in a way understandable to a layperson. So that means somebody just off the street who doesn't necessarily know anything about calculus or even maybe any college algebra. So what this means is if we price the item at $10, we will sell 240,000 of the item. So this is just interpreting what a function means. So this is probably, or at least hopefully, something you have some familiarity with from a pre-calculus class. Now the new thing is to interpret the derivative. So what does this statement f prime of 10 equals minus 29,000 mean? Well, this is our rate of change. So this is interpreting if we change the price from $10, how does it impact the sales? Well, if we think of this for a second, what does F prime look like? Well, this is really dq dp. So it's saying if I change my price, how does it impact the quantity? So we can phrase this as if the price of the object is $10, that's where my 10's coming from, that's what I'm plugging in. And now I want to change this, so I can think of this negative 29,000. I can think of this as negative $29,000, negative 29,000 over 1. So this is the units sold, and this is the dollar amount. So if I increase the price by 1, price by $1 to $11, well, then the number sold should go down by about 29,000. Remember, this is all approximately. Right, so increasing the price from $10 to $11 is going to result in about 29,000 less units being sold. And then if you're an economist, you have to determine, well, is that still beneficial? So if I raise the price by $1, am I still making more money even if I sell less units? Let's try one more example of how we can interpret the derivative, and we'll try to make sure as the semester goes on we stop and make sure we're interpreting what we're doing with word problems as well. So let's let W be the amount of water in a container, let's say measured in gallons, in a container. Depending on time t. And then the time we'll say is measured in minutes. Okay, so for the first thing, let's just interpret what are the units. Knowing what the units are can often really be useful in giving an interpretation of the derivative. So what are the units? Well, the units of W are gallons, and the unit of time is minutes, so this should be gallons per minute, right? So it's the units of this divided by the unit of this. So gallons per minute. And now let's do a few more interpretations here. So let's suppose at time, say t equals a, the container is full. And then suppose at some time t later, with b bigger than a, we open a valve and let water start leaving the container. Okay. So our first problem for times t between a and b, let's say is dw dt positive, negative, or 0. Well, we know at t equals a, the tank is full, and we don't open the valve until time t equals b. So the amount of water is not changing at all during this time. So the amount of water is not changing. So that would mean dw dt should be equal to 0, because there's no change in the amount of water for that time period. Okay, so what about for times t bigger than b, but before the tank is empty? Well, in this case, now the water is leaking out. We're not adding any water, so the amount of water is decreasing. So dw dt should be less than 0 because the amount of water is decreasing. So as time goes on, there's less water in there. So if you think of this as like some time in the future, so say like t0 is bigger than b, well, dw dt is approximately w of, say, t0 minus w of b over t0 minus b, but this number here is negative. This is less than 0 because there's less water at t0 than at b. So our derivative here is negative. And what about for t after the tank is empty, or the container is empty? Well, again, there's no water changing, so this is again just going to have dw dt equals 0 because there's no water in there, but the important point is the amount of water is not changing, so the derivative is 0.